So these are the contents. At first, I will just give you an overview of the types of projects that can be dealt using this software, and then we'll move into the features and interface of the software, and then we'll have a software demonstration. So I have some models ready with me regarding the excavations, the soil structure interaction between, integration of the structural model with the geotechnical model, as well as some tunnel models. So we can have a discussion on them, demonstration. Okay, let's start with the application areas. So this software can be applied into the foundations, so ranging from the shallow foundations to deep foundations, and even dealing with the complex pile drive foundation. And since you were talking about the validation of the results, at first, in order to calibrate the model before the start of your real project, you can always do the driven pile test in the software, so that you can calibrate your inputs in the software and then proceed with the real project study. So you can do such kind of calibration followed by the shallow or deep foundations, and ranging to the complex pile drive foundation as well as well or caisson foundation. So you can do all such kind of analysis in this software. And then so slope stability. So this is the second application. So generally slope stability, like a project, is like a part and parcel of almost all kinds of project. So you will have slope stability. You can in the tunnels, in the tunnel project, in the excavation project. So the important thing is it is always needed to have the factor of safety and then failure surface at each and every construction stage. Suppose let's say you're dealing with an excavation project like this, maybe a retaining wall at the end of the construction, and you would like to find the factor of safety as well as the failure surface at each and every construction stages. So that means in one single model, you can able to get the failure surfaces and the factor of safety at different stages of excavation. So that will be very much helpful in order to understand the behavior, because this will be just an additional tool after the additional application that you want to do in the real-time project. So after the excavation, maybe you want to go for the retaining wall, or you want to apply some service conditions like a traffic load, or as well as the rainfall. So all such things can also be applied in the same model itself. Then you can apply the software into tunnel. So in the case of tunnels, you can go for hilly terrain tunnels, wherein the entire undulations of your hilly terrain can be captured easily. So modeling of this kind of hilly terrain is very easy using this software. I'll be showing you the list of features that will help you out in modeling this kind of things. And then you can even model the fractured mass. If you can model the joints using explicit as well as implicit kind of techniques. So that will be helpful in understanding the behavior of your tunnel in that kind of real-time situations. And then the portal stability, so as well as infrastructure, or you can consider this kind of model very similar to your energy storage scenarios. So you can do that kind of modeling in this software. And in tunneling engineering, the entire behavior of the tunnel is widely dependent on the type of excavation method we do. So it's a shield TPM method or NATM method. You can apply that kind of methods very easily using the software, because it's just a construction sequence that we are defining in the software, and whatever that kind of sequence that we are really interested in can be easily simulated here. And then of course you can integrate with your structural tool. Suppose let's say you have a Midas civil model wherein you have bridges at the top of your ground, and then there is a proposed tunnel being excavated. So you can simply bring your a model from civil to GTS NX, and you can model the excavation directly in the software GTS NX. So the tunnel excavation, how that is going to affect the existing structure can easily be simulated. And if let's say if you do not have any structural model ready, you can simply model the structural the piers or the deck using the like all the structural tools that we have in GTS NX as well. So you can use beam element, or you can simply go for solid element. All such kind of things can easily be simulated. So these are some kind of results that you get. So this is about the tunnel failure surface. So tunnel portal failure surface, the stability of the portal. And then we have a shaft here, and then there is a TBM lowering at the bottom. So there will be a TBM lowering, and you can simulate the TBM excavation here. And this is a very simple demonstration model wherein you have a deep excavation nearby your tunnel. So you can the metro station excavation, kind of. And this is the NATM approach, wherein just after excavation, you're letting the soil to have the residual displacement, the volume loss. You're actually letting the volume loss, and then later on you'll be applying the primary as well as a secondary linings. So that kind of simulation can easily be done. And the next application is excavation. You can apply this software in all kinds of excavation lateral support systems. Suppose, let's say, if you want to if you're interested in applying the diaphragm wall, you can go for it. You can go for sequent pile technique. You can apply the struts. You can apply veilers. You can apply the plex and so on. So there is a lot of scope here. You can go for anchors, grouted and ungrouted as well, and combination of both. So you can apply all such kind of techniques here. And since this is a 3D model, so you can consider the 3D effects and all the non-uniform excavation and more stress concentration at the corners. All such kind of things can easily be captured. Then you can apply this software in hydraulic and underground structure. You can go for the concrete gravity dams. You can go for embankment dams or CFRD dams and do the seepage analysis, do the stress analysis. And then you can combine the stress with even the dynamic analysis scenarios. So all such kind of analysis can easily be done. And you can apply the software into mining as well. So since you are not into mining, I will just give you a rough idea. You can go for open pit mines. You can go for local slope stability or a global slope stability of your entire mine. And then you can understand the vulnerable areas at different zones of your model. And suppose there is a cavern being constructed just underneath your open pit, then how the entire stability can be checked. So that kind of scenarios can easily be captured. And the underground mining roadways. So this is very similar to your tunnel model. You can go for the steel drapes, shotcrete, or the entire segment lining, or you can go for rock bolts and so on. So all such kinds of analysis can easily be done. And the next and last application is the soft soil and embankment. So let's say you're dealing with a road infrastructure or roadways, and wherein you face a clay soil, or that, and the London clay, as you know, is one of the most interested study being done by many of the researchers around the world. So London clay kind of things can easily be simulated, and then you can go for a PVD technique, or you can go for sand compaction piles or gravel compaction piles. So all such improvement techniques can easily be simulated, so that the settlement versus time, as well as the pore pressure versus time, can easily be understood, so that the consolidation behavior and the improvement scenarios understood. And then this can be combined with your embankment, and embankment slope stability can also be checked after and before consolidation. So that's one of the application. So let's move into the product. Bobby. So that's regarding the application. If you want me to like answer any of the questions regarding to different application areas, let me know, so that I will tell you like whether the software is applicable into that application or not.
I think you've covered more or less the typical applications that we use finite element modeling for. So that's the kind of stuff that we do with Plaxis
Perfect.
at the moment. So yeah, the focus is to why would Midas be better? That's what we're
Sure.
interested in hearing.
So
Yeah.
that's now I will be focusing on. So I will be now focusing on the interface and GUI, basically graphic user interface, and the features that will help you out in achieving the modeling techniques that you want to do. So at first we'll see the product. So this is a product that we are offering for. So GTS NX generally provides a platform. It's not like 2D modeling or separate to the license, or 3D modeling separate license. So when you have a GTS NX, we are actually having a platform wherein you can do both 2D modeling and 3D modeling, as well as accessibility. So we are actually selling you a platform, and this kind of all the kinds of analysis. So basically, all the geotechnical modeling can be categorized under three main scenarios. One is axisymmetric, 2D modeling, and 3D modeling. So all the three kinds of modeling can easily be done using this software. And this is how the software looks like. So you can see this is a work tree. So whatever work you do from starting to ending will be registered over here. So you can edit, or you can change the input values, or you can change the load values, or you can change the material inputs anytime using this work tree. And this is a ribbon menu. So let's say you're dealing with geometry. So you want to create a geometry. You can use all the kinds of functions that are available here, create a geometry. And then you can move to the meshing, wherein you can create the input material properties and mesh the entire geometry to finite elements. And then you can choose a type of analysis that you are interested in, and then run the analysis, get the results. So as simple as it. So that's how the ribbon menu is arranged in segregated. All the commands are segregated in such a way. And the one and most important thing is in Plaxis at a time you can only open one model at the same time, but in GTS NX you can model or open n number of models at the same time. So there is no limitation in one single license. You can in one laptop you can open n number of models at the same time and analyze n at the same time. So the important thing is if your hardware is capable to analyze 100 models at the same time, yeah, you can do that using the software. And this is a basic workflow in this software. So generally all kinds of finite element tools use this kind of workflow. Suppose let's say you're having like a GIR report as well as you're having the investigation report and the survey report with you. So you can create a geometry using that, or else you can simply import the geometry. So there are various CAD like integrations formats in GTS NX. You can import most of the CAD integrated formats, or else you can simply create a various geometry using the tools present in the software. But in Plaxis, what you do is you start with the borehole data. So you always start with the borehole data, and then you need to modify the geometry in Plaxis. So that's a little tedious task, but you can do all the things from starting. Either you can use the borehole data, or you can simply use the manual commands to create the layers as well. Then we use a GIR report and the different calibration inputs, and then we provide the material properties, maybe a more column or a modified camp clay or a hardening soil and so on. And then we create a properties. So since this software supports both 2D and 3D modeling, you have 1D properties, 2D properties, as well as 3D properties in this software. So you can use them for the analysis. And then you can discretize your entire geometry to a mesh, so using various kinds of elements. So the important thing is in GTS NX we have not only tetrahedral elements, we have like hexahedral elements as well. So I will discuss about that here in the meshing tool. And later on you can go for loads and boundary condition definition, run the type of analysis that you're interested in, like the construction stage analysis or simple C-page analysis and so on, and get the results accordingly. So this is a basic workflow. So I will start with the geometry. That means my presentation from now onwards will proceed this workflow. So let's start with the geometry. Yeah. So as I said, in Plaxis, you always start with the borehole data. But in GTS NX, you can either start with the borehole data, or you can simply do the manual commands as well. So you have an extrude option. You can create this entire solid using the 3D coordinates, or you can simply extrude it using the plane that you form using the manual polyline or line commands. And the important thing is all the functions that we have in the geometry tool of this software is very similar to the CAD software. So if you're familiar with the CAD like a software, then it is easy to jump into GTS NX and model all the stuff in this software. And then let's say you're dealing with a tunnel which is changing its direction along the length. In such a case, in order to model this kind of tunnel, the modeling this particular part generally takes a lot of time, because we need to know the direction, we need to know the section, how is it orienting and so on. But here we have an option called sweep, wherein you can simply provide a section and provide a guide curve how it is moving along the length. You can simply extrude it along the guide curve. So that's one of the important things. And as I said, similar to AutoCAD, we have various commands like a trim, divide option, and so on. And this is very important. We have like Boolean operations as well, and we have an automated Boolean tool as well, which we call it as AutoConnect. Suppose let's say you're dealing with hundreds of solids in your tunnel, like there is a tunnel model. You have the main tunnel, the cross tunnel, and the fire exits as well. So the important thing is each and every solid should be interconnected. Only then the nodal connectivity will be there, and only then the proper stress transfer would happen. So, but like connecting each and every solid individually is not always possible. So in that case, what we have developed is the auto connect option, which is the Boolean operation, which is automated. So all you can do is you can simply select all the solids at once, and then every solid will be connected by simply clicking one click, which is the auto connect feature. By this, all the solids will be connected, and then you will have a full control over the solids or geometry that you have created. And then you can mesh each and every solids with the different sizes as well. So that will be very much helpful during the meshing. I will come back to that in the meshing tab. And then we have an imprint option. Suppose let's say you're dealing with piles and you want to model the pile as a beam element with some normal and shear stiffness. In such a case, you can simply use the line element, and that line element should be interconnected with your solids by using this imprint option. And we have an important tool called terrain geometry maker. So like let's say you're dealing with a hilly terrain like this kind of scenario, and you want to model a particular area. In order to model this area, you need to have various kinds of inputs, like let's say you have a contour data, or you might have the lidar survey data. So you can simply input all such data into this software. Suppose in the case of contours, you can simply import the contour data, and then software will create the surface for you. And this surface creation is done by Terrain Geometry Maker. And once this terrain is created, you have the entire terrain developed. Now, all you need to have is the stratigraphy, the layers data. So you can import your entire bedding planes, or you can import the borehole data into the software, and then software will create the bedding planes, or else you can manually input all your borehole data. And using this bedding planes as well as the terrain, this model can be created within very less time. So the entire process of developing this model will take less than 5 minutes if all the data is ready with you. Then we'll see how this software is interoperable.
Sorry,
And
Harsha, sorry, I was
yeah,
just a question on geometry.
yeah, please go
Can
ahead.
you import geometry from a CAD software like Civils 3D or
Yeah, we
other
have various
AutoCAD?
CAD formats. Yeah, we have
Okay.
various CAD formats inputs. Like let's say you're dealing with CAD software, you would like to import, like let's say the DXF2D, DWG, or DXF2D or 3D. And in addition, there are other CAD formats as well. So you can simply go to this CAD and you can go for either Parasolid input or ACIS, HTEP, IGS, ProE, CATIA, SolidWorks, and so on. So there are various CAD formats that is
Hmm.
possible to be imported into GTS NX. So the modeling is made very easy. Either you can import the geometry or you can create it in the software. So that's up to you,
Okay.
whichever way you like.
All right. Thanks.
Yeah. And other like interoperability with this software is with the structural tools of Midas. We have a Midas Gen, which is a building and analysis and design tool, and then a Civil, Midas Civil, which is a bridge analysis and design. What you can do is you can import this entire models into GTS NX. You can import the reactions of these models into GTS NX, and then instead of modeling the soil as a spring, you can simply model as a continuum soil. And then once the continuum soil is modeled, you can provide all kinds of constitutive models to it. You can go for hardening soil, which is mostly replicating your behavior that you're interested in, or you can simply go for moculum, or you can go for Hochbrunn material if there is a rock, and so on. So that once you do the stress analysis in this GTS NX, you will get the springs. So because you will get force and displacement that can automatically be taken into Civil and Gen using 1 or 2 clicks. I will come back to that in the demonstration. So
All right.
basically, the Spring data generation has been automatically created because we are actually taking the model of the superstructure along with the reactions that you're finding in superstructure. So that's the important thing.
Thanks.
And then you have the supported CAD formats. So yeah, so let's talk about the SSI, which I'm talking earlier. So that's regarding the Spring data generation. Suppose let's say SSI is nothing but the interaction of your stiffness and deformation between superstructure and soil. So if the flexibility or the stiffness of your soil is different, the like reactions or your the bending moment or shear forces in the deck can also be different. So that's the reason SSI is very important in high-rise buildings or heavy structures like your bridge. So that entire thing has been made very easy using this interaction between the GTS NX as well as structural tools. Suppose let's say you have a bridge generated in Midas Civil. Your structural team is using Midas Civil, let's consider, and they have created a like a cable stayed bridge as shown here. And now we need to provide, as a engineer, we need to provide some spring data to it. So what you can do is at first we can ask the structural team to go for some analytical spring data inputs, or you can ask them to go for fixed supports or based on the interest. And what we can do is we can bring an entire model from Civil to GTS NX, and then we can model all the soil continuum over here. We can even incorporate the explicit joints, or we can provide a different material inputs like a hardening soil or maybe different kinds of material inputs. So once this kind of inputs is created, we are not actually restricting the soil behavior to elastic, but we are actually considering the plastic behavior as well, because that's the importance of the geotechnical tool. So once this modeling is done, we can take the reactions from Midas Civil to GTS NX. So these reactions could be the envelope of all the load cases, or can be an important load cases reactions. So we can take that into GTS NX. And then once the analysis is done, considering the reactions from the superstructure, we will get the force displacement curves. And this force displacement curves will now be transferred to Midas Civil, and that will act like a spring data here. So this process is automated, like with around almost 2 clicks, the structural model will be imported into GTS NX. Again, with the 2 clicks, the reactions will be imported. And again, with the 2 clicks, the force displacement curves will be transferred to Midas Civil. So this process is an iterative process, while like if you do twice or thrice, the results will be converged, and then you can proceed with the design in Midas Civil. So this is the thing that will be very much helpful in case of the soil structure interaction study that you are interested in, and which will be very much helpful in the case of high-rise buildings or the heavy bridge structures. So if you have any question on this, let me know, then we will go ahead.
Oh, that's what I asked at the very beginning of the presentation. That's so yeah. Maybe if we can look at which other Midas packages NX can interface with.
Yeah. So we can go with Midas Civil and Midas Gen, and we have another software that is Midas Engine, which is similar to Gen. Even we can bring all that like the superstructures from the Midas software into GTS NX. So basically, all the structural tools that we have with Midas, all the models from them can be imported into GTS NX.
Okay.
So that's the idea, because we are actually in a finite element company. So since we have developed the finite element software solver, we apply that solver to structural analysis. We apply the same solver to geotechnical analysis. So the environment has been the same all the time. So it is very easy for us to import or export the geotechnical model from structural to geotechnical software, or from geotechnical software to structural tool. So the two-way import and export is always there. Okay, so that's regarding the geometry model and the soil structure interaction. Now we'll move to the materials. What are the different types of materials that we have in this software? So we have elastic material, we have plastic materials as well. So let's say you're dealing with the soil, you can go for in the case of preliminary analysis, you can go for Moog Coulomb or Duck appraisal. If you want to deal with the rock, you can use the Hook-Brown or generalized Hook-Brown material models. For the case of clay, you have modified camp clay, soft soil creep, and like advancement to the Moog Coulomb is modified Moog Coulomb, and the advancement to this modified Moog Coulomb is hardening soil. And then we have hardening soil with small strength stiffness as well. And since you're also interested in dynamic analysis, let's say you're interested in liquefaction study, in that case, you can go for modified UBC sand, or you can go for PM4 sand. And in case of static liquefaction study, you can go for North sand as well. And let's say you want to consider the hysteresis study of the model. In that case, you can go for hardened Greenwich or Ramberg Osgood, or hardening soil with small strength stiffness as well. So basically, we have a huge list of material models. You can use these different material models for different requirements. So once the requirements are set, you can choose the material model that is helpful for your case, and proceed for the analysis as well. In addition, you can use the undrained materials. So this is very similar to Plexus, like undrained EA, B, C. So the same thing, that's a generalized thing. So we have used the same thing for the similar to Plexus, undrained A, undrained B, and undrained C. And in addition, you can use the unsaturated material properties as well. That will be very much helpful in order to understand the seepage behavior more realistically. So that's about the material. So once the materials, like now the geometry has been defined, and then you have like inputted the material data. Now we need to input the properties for the elements. So let's say you're interested in dealing with the 2D models, wherein the excavation wall is itself the beam element. You can go for a beam element or embedded beam element, or you can go for truss element or embedded truss. And for the case of ground improvement, you can go for geogrid as well. And in order to determine these, like let's say apply the spring shear stiffness as well as the normal stiffness, you can go for the pile interface as well. And in 2D elements, we have geogrid 2D, we have shell element, plane strain, plane stress, and so on. So you can apply this to get the like structural results as well. And then you have a solid property for a 3, wherein you can go for tetrahedral elements, hexahedral elements, and even pyramid elements as well. So I will come to that in the next stage. And we have various applicable elements like the interface element, the rigid link, the pile tip for tip bearing capacity, and so on. So this will again helpful in order to model the required behavior the client or the user is interested in. Then this is the section property database. So let's say you want to determine like input various sections. You have a huge list of sections according to different codal provisions as well. So you can simply use the type of codal provision that you are actually dealing with, and the entire the like flange width, the depth, and everything will be taken from that database. And the structural properties such as the moment of inertia, the torsional coefficients, everything will be automatically calculated. So there is no need to again deal with your structural engineer. And then you can go for the axial metal sections as well. So in the case of excavations, what we have observed is most of the Southeast Asian countries and some of the European countries are using the axial metal sections. So we have incorporated the axial metal sections as well. So you can use these sections and then proceed for the application of the section to the beam element and go for the analysis. In addition, we have the SRC sections. So steel reinforced concrete block. You can go for SRC box, or you can go for SRC pipe as well. And suppose, let's say you are dealing with such a kind of section which is not coming into all these categories. In that case, you can go for the complex cross-section property generator as well, wherein you can simply create your own geometry that is actually relevant to your real section. So you can simply create that, do the mesh, and software will calculate all the structural properties for you. And you can use this for your beam section or truss section and proceed with the analysis. Then that's about the section database. Now what we have done is we have created the geometry, then we have applied materials and properties. Now we have to mesh that geometry now. So we have to discretize the entire geometry to some finite elements. So we have various features for that. So we have 2D auto mesh, so which is more like an unstructured mesh, as well as 3D auto mesh, which is more like an unstructured mesh. But if you want to go for a structured mesh, we have 2D and 3D map mesh as well. So this will be very much helpful if you want to have the local coordinates of your entire elements aligned. So this will be very much helpful as well. And then, as I said, initially we have an option for auto connect to connect your entire solids with your adjacent solids. So when you do that, what the software can understand is it will differentiate the length and dimensions of each solid separately. And because of that, there will be like while meshing, you can able to find a fine mesh here and coarser mesh at the boundary. That means the adaptability of coarser mesh to finer mesh will be automatically considered. There is no need to provide the seedings and so on. So software will automatically adapt to the mesh size. And then like let's say you're suppose you're dealing with a 2D model and all of a sudden you want to consider a 3D behavior of the model. In such case, you can extrude your 2D mesh to 3D, not the 2D geometry to 3D, but actually you're able to mesh like extrude the 2D geometry to 3D as well. So this will be very much helpful just to save time of developing a 3D model altogether. And then this is the important advantage over Plaxis. So we have a hybrid mesh here. In Plaxis, we only have a tetrahedral mesh, but in GTS NX, we have a hybrid mesh wherein that is having hexahedral elements, pyramid elements, as well as tetrahedral elements. So what is the advantage, you may ask me? The main advantage is the computational time. So let's say you're having very very different geometry and very complicated geometry, and you're using tetrahedral elements for the entire geometry. In such case, the number of elements developed in the model is huge. You might have 200,000 or 300,000 elements. So when the number of elements are more, the time of analysis is more, the computational time is more. But in order to reduce it, we have a hexahedral elements, wherein these hexahedral elements can be very much helpful to occupy more volume and provide even accurate results because number of nodes are very high. So it will the when you use say hybrid elements, the like a number of elements are low and the computational time is very fast, and you can have the analysis in very less time when compared to tetrahedral elements. So this is one advantage over plexus. And as you know, the hexahedral elements are more accurate than tetrahedral elements because of sheer number of more number of the nodes. And in addition, you can use the higher order elements as well, wherein you can go for mid-side nodes to have more accuracy in the model.
So Harsha, do you so you can select what kind of element you want to use, or is the software automatically selecting the best
Yeah, so
type of
like
element?
yeah, overall we have two measures. One is tetrahedral measure. So when you use tetrahedral measure, every geometry will be having tetrahedral elements. But when you use the hexahedral, so when you use this hybrid mesh, what
Yeah.
happens is wherever you have the uniform solids, the hexahedral elements will take the entire volume. But whenever you have undulations like this, which you are seeing in here, these undulations generally cannot be adapted by the hexagonal elements. You will have various gaps over there. In order to overcome that, these undulations will be taken care by the tetrahedral elements, and those tetrahedral elements will be in contact with your hexahedral elements through the pyramid. So that means in one model, you're actually having all the kinds of elements.
Right. Okay.
So based on the size, mesh size that you give, you may have 80% of hexagonal elements and maybe 10% of tetrahedral and the rest of the other elements. Or if the mesh size is high, then that ratio may differ. But you have an option to choose between tetrahedral and hybrid mesh. Okay.
Okay.
Yeah, so that's regarding the mesh. And now, like once the meshing is done, you can apply the loads. And important thing is you can apply the load onto the geometry as well as onto the mesh as well. So sometimes what we do is we apply the load on the mesh, and all of a sudden we need to like reduce the mesh size and so on. In such case, if we delete the existing mesh, then the entire load will be deleted. So in order to like overcome that feature, we have an option to go for the like a load application on the geometry itself. So even the mesh is deleted, there is no issue because load has been applied onto the geometry. So when the analysis is done, the load will automatically be transferred to the mesh, and you can get the results accordingly. And in the case of loads, you can go for concentrated force, concentrated moment, and even concentrated displacements as well. And you have an option to go for initial equilibrium force. So what is this? I will tell you right now. So the thing is, in situ stresses in the soil plays an important role, and in situ stresses can be determined by using various techniques like K-naught technique or gravity techniques and so on. But let's say if you're dealing with rocks which is having huge in situ stresses, in that case you can go for initial equilibrium force. You can simply input the like a stress that you calculate or you get from the investigation team, and you can directly apply the initial stress that is present in the soil or rock, and then go for the analysis accordingly. And the important thing is you can apply the like you can combine all the kinds of loads using various factors, and you can apply the combination load. So the important thing is there is no codal provisions in this software, but you have all the loads that you can apply. So based on the codal provisions, you can apply the factor manually, and you can get the combination load. And once the combination load is achieved, you can run the analysis and get the results accordingly. And another thing is the dynamic loads. In the dynamic loads, you can go for the seismic loads, you can go for blasting load, you can go for machine load, basically the sinusoidal load, and you can even go for train dynamic loads as well. And that those are the time history loads. And if you want to go for the response spectrum, we have a response spectrum like a database present in this software. Like you can choose the response spectrum of various earthquakes present in the software, or you can simply choose the design spectrum according to various codes present in the software. So you can do the response spectrum analysis, you can do the time history analysis, you can even do the eigenvalue analysis, and so on. Now,
That's very interesting. That's very interesting. The option of um, using spectrum
yeah,
because Fluxys can't do that. It can only do like time marching explicit analysis using a time history of acceleration, but it doesn't take
Yeah,
spectra as inputs. So that's interesting.
yeah. So the important thing is we have the database for the earthquakes as well. So since we have the database of various earthquakes, you can even take the response spectrum of these earthquakes and get the analysis done. Or else you can simply create the design spectrum of according to various codes, and you can use that for the response spectrum analysis as well. So that's up to the like a user. Yeah. Then we'll move to the finite element analysis. So what are the different analysis this software could do? You can do a static analysis wherein you can go for linear static, or if you want to consider material nonlinearity, you can go for nonlinear static analysis. And then you can do a slope stability analysis wherein we use the SRM technique. So this is the same technique which is being used in Plaxis as well. In Plaxis, it is called a C5 reduction technique, but here we call it strength reduction technique. So both are one and the same. And then we have another method called the strength analysis method. So this is one of the important method that will be very much helpful in order to determine the local slope stability for your case. So what happens in this method is in the traditional limit equilibrium method, we develop various slip surfaces, and we need to calculate the stresses at the different slices using Bishop method or Felinius method or Yambo method and so on, right? But here, instead of using the Bishop method or Felinius method and so on, in this software, we actually use the finite element method. So stresses are calculated according to the finite element method, but the slip circles are given according to the limit equilibrium method. So we can say it's a hybrid method, which is using the combination of FEM and LEM, FEM analysis and LEM like slip data generation. And another thing is you can do this entire analysis in construction stages, so that in each and every stage you can able to get the results of a factor of safety and like failure surface. In addition, you can do the dynamic analysis, wherein let's say you want to determine the frequencies of your model. You can go for eigenvalue analysis, or else if you want to simply do the response spectrum analysis, you can go for response spectrum analysis. If you want to calibrate your model using the 1D 1D ground response analysis, you can do a 1D ground response analysis. So this is the same thing which you might have used using the deep soil or Shake software, Shake 2000 software. So in that software, there is an option called the 1D ground response analysis. You can do that directly in the software itself. And we have a 2D equivalent linear analysis as well. So this is addition to the 1D ground response analysis. And the more detailed analysis, such as a linear time history, both the direct and modal, or else nonlinear time history analysis as well. So nonlinear time history analysis can be done. And there is one more addition to it. You can couple your nonlinear time history with SRM analysis. So you can, like, let's say you're dealing with the hilly terrain, or you're dealing with the excavation itself, let's say, and you applied an seismic load over there. And at the end of earthquake, or maybe during the earthquake, you want to study the slope stability of that particular like a slope or particular excavation area. You can couple your SRM with this linear time history, and at a particular time of your interest, you will get the factor of safety and the corresponding failure surface as well. Then you can apply the seepage, and you can do the seepage analysis, wherein you can go for steady state seepage or transient seepage. So in the case of transient, you can go the variation in your water levels, like gradual increase in the water level or a sudden drawdown condition. So all such conditions can be simulated. And then you can combine your seepage analysis with the stress. So basically coupled analysis can be done using a stress seepage semi-coupled as well as fully coupled analysis. So this will be very much helpful because like in real time, what happens is as the deformation is happening, your permeability of the soil at that condition is actually changing in real time. So as the deformation changes, the permeability changes. And again, as the permeability changes, the deformation variation takes place. So it's a time dependent analysis. So you can get the real time, I won't say real time, I would say the real time approximation easily captured using the coupled analysis. Then you can do a consolidation analysis, as I already explained. And all these analysis that I have explained till now can be done in construction stages as well. So as you know, soil is a highly nonlinear material. So with the change in the stress, its behavior changes. It may move from elastic to plastic very easily. So such kind of things generally we can consider when we do it in the construction stages. Of course, we can do it in the static direct analysis as well, but we need to provide some increments. But here you can actually provide the excavations in increments as well, and deactivation and activation of your struts in different stages. So basically, the phase analysis which you do in the let's say plexus. And one more important thing is you can use the thermal stress analysis. So with this, you can go for ground freezing technique, or you can even provide provide fire in the tunnel. So fire in the tunnel kind of analysis can also be done. So this the entire analysis that is possible in GTS NX. So if you have any questions here, let me know. Then I will move to some advanced tools that are present in the software.
Let's move on to. I mean, just obviously the question is speed, right? So
Yes, yes.
you can do very complicated stuff, but if it takes a month to run any of the models that you're showing on screen, then you might not have that time in your program.
Correct. Yeah,
So
correct. So
how does it benchmark with compared to a similar model done in Praxis, for example? Is there a way so
okay.
that the software is quicker?
Yeah, there is a huge advantage in the case of computational speed when compared with Plexus. I will show that now. So let's say I have this model. So this entire model may just take me a very small time, like maybe 10 to 15 minutes, wherein you have various construction stages, and the stages of excavation is different, and the rock walls are different. So why it may take very less time for me, because of the options that I provide. So we have an option to go for the number of processes. Suppose, let's say in my PC I have around like sorry. Yeah, here I have around 16 logical processors, so I can directly ask the GTS NX to use entire 16 or just 10. So whenever you provide more number of processors, the analysis time will be lower. And one more thing is the solver. The FEM solver actually has different kinds here. So let's say this multi-frontal solver. So what happens here is the multi-processes that you are providing will be easily used when you go for multi-frontal solver. So in the case of dense and AMG, it's like using like a single processor, or based on the mesh and so on. So if the model is very heavy and there are a huge number of degrees of freedom, see, the software automatically moves to a multi-frontal when you choose the auto, or else you can simply choose the multi-frontal solver automatically. And then in addition, we have a graphical processing acceleration. So I can even use the graphic card acceleration as well. So using this, the analysis time will be even enhanced, because there are huge number of processors, thousands of small processors in the chip. That will be helpful for the analysis. And so these are the two main things. And one thing is, if your hardware is an SSD drive, uh, give me a minute. Okay, so this is not, I cannot see SSD drive here. But let's say if your hard drive is not HDD but SSD, then your analysis time will be even much higher, because in the case of SSD, the speed of communication between the software and saving the files will be very much higher when compared with the traditional HDD drive. So if you have SSD, then the analysis time will be even like even better. So using these options, the analysis time will be made very less when compared to Plexus, because in Plexus the software automatically takes the processes. We as an engineer do not have any control on the number of processes that we provide.
Hmm.
And
Can I
as
ask
you
you something on this?
yeah, please go ahead.
Does GPU acceleration work with Intel GPUs?
Yes, it works with Intel GPU, but there is one catch here. You need to have at least two graphic cards in your software. So one graphic card will take regarding the graphics. That means Intel, let's say there is an inbuilt graphic card here that will take control of your graphics in the model. But for the computational purpose, uh, for the computational purpose, you need another card. So in your laptop or in your PC, you should have two graphic cards. One can take care of the graphics, and other will take care of the computation. The
Eh,
processing can be taken care. So you can
So
use the NVIDIA, you can use the Kepler, you can use. We actually support NVIDIA cards, but Intel is also fine. But we recommend using NVIDIA GeForce graphic cards.
I was talking about just the computation.
Yeah.
So can the computation run also on an Intel graphics card, or the Intel graphics card will be there only for the traditional scope of works, which is the visuals?
Yeah, so generally, like as I said, like if you have two Intel graphic cards on your PC, then you can able to use a second graphic card for a computational purpose. But we do not generally
Okay,
recommend it. We recommend NVIDIA GeForce cards. And there
okay,
is another series like Tesla series or Kepler series. So we recommend that. We have a huge list of validation, not validations, like testings that have been done with various graphic card. We can share that card with that sheet with you, so that if you want to go ahead with the purchase, then you can use that sheet as a reference to use the graphic card on your PC.
okay. Thank you for that one. And the GPU acceleration happens while the stiffness matrix is solved, and the processor parallelization happens when the phases run in parallel. Is that correct?
Yes, that is correct. And I
Okay.
need to add something to that. So, let's say, in the advanced nonlinear analysis, you have various kinds of solvers, the stiffness updation schemes. So if you are using initial stiffness, that means whatever the stiffness matrix that is generated initially will be used for the entire analysis. But generally, that is not recommended for the geotechnical scenarios, because we are not dealing
Yeah.
with elastic material. And in order to update your scheme, you need to use the other materials. Suppose, let's say, in the case of modified Newton-Raphson, the stiffness updation will be done when you go for when there is a change in the model, when there is the load is activating, something is deactivating. In such a case, the software will go for new stiffness matrix generation. Or else we have a full Newton-Raphson method. What happens is, in each and every increment, the software will generate a new stiffness matrix. So what happens is, when you go for full Newton-Raphson method, the analysis time will be enormous. It will take more time. If you go for initial stiffness, the analysis time is very less. If you go for modified Newton-Raphson, yeah, it is intermediate. So that's how even the type of a solver will change the time as well.
And one last question on this. If, let's say, I have 10 phases which cannot be parallelized, each one comes after the next one, and I use hardware acceleration, I'm going to use improvement, I presume. But if I use a higher number of processors, will I see improvement if the
Yeah.
phases cannot be parallelized?
Sorry, I didn't get, what do you mean by paralyzed? I mean parallelized.
I mean that every phase starts from the end of the previous phase. It's
Yeah,
not
that's
that
correct.
I have one master phase and after that I have several options. So you calculate the master phase and all the options below that can can be
Okay,
calculated at the
now I
same
understand.
time because they have the same master phase. So
Yeah, I
if
now
I don't
understand
have
that.
that,
Yeah, so in Plaxis, you can only develop one tree, like one set of construction sequences, and in one stage, like on the, let's say, master stage one, you can develop some unplanned excavation stages. But here in GTS NX, we have an option to develop any number of trees. I mean, the phase set. This is a construction stage set, and in this construction stage set, I have many stages. Suppose you want to have a different kind of construction stage set, you can simply go for second construction stage set, and you have a different kind of stages. So as of now, there is no like a secondary phase, like in Plaxis, you have a first stage, and you may have one stage or two stage, and so on. So that thing is, as of now, is not present here. In the next version, you will be having the sub stages in the in for each and every stages. But for
okay,
now, you can
okay,
create any number of sets. You can create like, let's say, I will do one here. I can do three, four. So I can create any number of sets, and in each set, I can create different stages. I can go for two, three. So I can give any number of stages. So this
Okay.
is possible.
Thank you for that.
So by doing this, you can actually do the parametric analysis very easily, because I can copy the same stage and I can modify. Let's say this is not present here, I will modify this and something like that. So that's how the tree can be modified at any time, like whenever you're interested. Okay.
Thank you for that.
Okay, now coming to some tools which I had left off in the presentation. So we have some advanced tools in the model as well. So the first thing is we have a tunnel and modeling and anchoring wizard. So till now what I've said is we need to create the geometry, we need to create the materials, we need to create the meshing, all the things. But that entire thing has been, entire process have to be made manually, right? But here we have an option for wizard. So let's say you're dealing with the wizard. All you can do is you can simply input the tunnel material, tunnel dimensions, the type of material it is taking, and you can go for shotcrete and rock bolt material definitions and provide an excavation sequence. Everything is just an input, and provide some mesh size. The software will develop the model for you. So there is no need to create the geometry, then there is no need to create the mesh manually. So the entire mesh will be generated manually, and even the construction stages will be generated manually. And you can use that construction stages for analysis and get the results. So the entire process has been made. You can use two number of tunnels and different excavation sequences for each tunnel as well. So this is one such tool that will be automated, that will be very much helpful for your analysis if you're dealing with a very simple case and you want to go for 3D, because the entire modeling time will be reduced to hardly 5 minutes if all the inputs are available. Then we have another tool called blasting dynamic load generation. Suppose, let's say you want to use some blasting load, and there are many equations to develop the blasting load. So all you can do is you can choose the type of equation that you want to use and provide some charge density. So all these equations are generally used for the controlled blasting. So you can use them, and software will develop the data for you. So the force versus time, basically the impact within very less, and so that kind of thing can easily be created in the software. And you can apply this load at the particular point of your interest, and you can run the time history analysis, and you can understand the blasting load application as well. So basically, this kind of data generation by an is generally very hard to produce by an engineer because it takes more time, but that has been automated in the software because we have a database for that. Then we have a mining converter. Suppose, let's say you're dealing with it's not it's the name itself is mining, but this process can be used in other kinds of projects as well. Suppose you're dealing with a leapfrog and you have some models in leapfrog. So what all you can do is you can simply export that leapfrog data into a CSV file, and that CSV file can be imported into GTS NX. So all you need to do is just import it, and software will automatically consider the blocks that are present in the leapfrog as mesh in GTS NX. So basically you're importing the mesh into GTS NX. So once the mesh is imported, you can go for the type of analysis that you're interested in. Like maybe you can apply the loads, you can go for dynamic analysis, or you can go for the construction stage analysis, up to you. But let's say if you are a person who want to deal or play with the geometry, in that case you can import the geometry altogether, and you can play it with the geometry, and then using that geometry you can proceed with the mesh and so on. Sorry. Yeah. And there is one more tool present in the software, which is automated live load data for train loads. Suppose you're dealing with an dynamic load of a train, and traditionally the train dynamic load is such a kind of load which changes with respect to time as well as a space. So as a train move forward, according to the space it moves, the dynamic load changes, and according to the time it changes. So that kind of data generation is very tedious for an engineer. So we have an automated tool for that. All you need to do is select the type of train and provide the velocity of the train and choose the place from where it is going and like start to end, and then software will develop the force versus time. and at different spaces as well. So the software will be able to create the time dynamic load generation, and you will be able to do the like analysis accordingly. And even you can understand the stability of your embankment by coupling your dynamic analysis with SRM as well. So that is one more added advantage. I hope this will be helpful for the HS2 project if you're dealing with that. Yeah. Then let's say so that now the analysis is done. So what are the type of results that you may find in this software? So you can get graphical results, you can get a contour, sorry, you can get the animation results, you can get the like let's say contours here, you can get the section diagrams even on a shell. So generally in a shell you only get the contours, but at a different section of your interest, you can even find the the section diagram, like how you're seeing on the screen right now. And then tables can be created. You can export the tables to Excel sheet. You can get the graphs directly in the software as well. And moreover, you will get the 3D PDF. So this is a 3D PDF that will be that might be helpful for you when you're dealing with your dealing with the meetings with your clients or fellow like colleagues. What you can do is you can simply export your entire model to a 3D PDF, like how you're seeing here. So you can able to see the geometry, dimensions. You can able to see the type of mesh over there. You can see what type of elements that are used and material properties. And moreover, you can see the type of results as well. So you can able to see the dimension, sorry, settlements, stresses, and even the slope stability as well. So that's very much helpful because all the times we cannot take the software and model along with it. You can simply export the results and the model to a 3D PDF, and you can present that in the meetings accordingly. Then we have another tool called Excel report. So what you can do is generally you can select the type of results that you're interested in, and the view that you are interested in seeing the results, and the like a construction stages in which you want to see the results. So the software will develop this Excel report for you. So this Excel report will act like a small part of your entire engineering report. So by which your time to take the snapshots for each and every stage and each and every result will be drastically reduced. So yeah, on a whole, yeah, this is about the software in a brief way. I hope I didn't bore you guys, but let me know if you have any questions, and then we'll move to some demonstrations.
Yeah, thanks, Harsha. And it's been very useful, and you've gone through a lot of things that we were interested into hearing about. And just one quick one from me. I mean, Plaxis has got another tool which allows to simulate soil testing
Yeah, we do have
on.
the
Yeah,
soil
do you
test.
have the same?
Yeah, suppose let's say this is the mode. I will go. Yeah. So here in this tab there is a visit. As I said, there is a tunnel modeling, anchor modeling, and the visits. In addition, we have soil test result. Suppose let's say you want to deal with the soil here. This is the initial stress considered, and only one stage for now I'm going to do it. It means in general you have different stages for a triaxial test if you want to. So you can choose the type of analysis that you want, a triaxial test, oedometers, CRS, DSS, and so on. So I will just add this stage, and then in actually you can choose the type of results you wanted, but by default you will get the following results. I will run this model. So now the solver has been and we'll close it. So these are the results. Let's say I want to see between Q and P. So this is the Q and P results. If you want to see between sigma 1 and sigma 3, or if you want to see the dilatancy, like let's say, yeah, this is one result. If you want to see between these two, you can see this result. So basically you will able to see these results, and you can even get the grid data. You can use this grids, and basically your soil test results will be very much helpful in order to calibrate the inputs, and using these results it will be easy to calibrate the results. You can
Okay.
copy this control C
Mhm.
and control V into your Excel sheet, and you can use that
Yes.
results data.
And how does Midas deal with large deformations? Can you simulate problems where you have large deformations? Because that's something that Plaxis struggles with when you start getting very large areas of failing
Yeah,
ground, if
yeah.
you like, it really struggles.
Yeah, so that's very important thing which needs to be considered. So the important thing over here is the traditional finite element tools generally cannot deal with the large strain problems because in case of large strains, there is no equilibrium condition happening over there. But in the finite element solver, each and every step has to be in equilibrium, and
Yeah.
that is where the implicit solver comes in. In the implicit solver, you will get the equilibrium in each and every stage, but when you go for large strain problems, there is an issue because the entire state of the model itself is not in equilibrium. So implicit solver cannot do it. But as of now, our solver is also implicit. So like traditionally, what we can say is we cannot say it because only explicit solver or the Lagrangian equations can able to take the large strain issues. But we have some options to take care of the convergence so that the equilibrium will be established and you can see the results accordingly. So such options include, wait a minute. Yeah, so the first thing is tolerance criteria. In Plaxis, by default, you have only the displacement criteria of 0.01. You can actually vary here in the software, or else you can use the enhanced initial stress. So whenever there is a huge stress or some stress concentration happening, it is better to use this kind of solver so that the convergence will be established and you can see the results. So all I'm trying to say is you're actually not simulating the large strain problems, but you are using the implicit solver and you making some changes to get the results for the large strain cases. And in case of direct analysis, we have an option for the arc length method and the displacement control method. So using these arc length methods, the convergence can be established very easily so that you can at least take care of the large strain issues. But but you have a very huge strain. In that case, yeah, this is not possible
Mm.
in the case of implicit solver, but you can understand the vulnerable zones. So that is there. You can understand the vulnerable zones, but how much it is getting displaced, that cannot be established using this software
Okay.
because this is
All
a
right.
traditionally an implicit solver.
Yeah. Yeah. Okay. Understand. Yeah.
Okay, any other questions?
Harsha,
Yes.
is there a programmatic interface to access the operations of the software, an SDK or even an API in any programming language that can essentially control the software through a command line or through
Yeah.
a script on the side? So Plaxis has the Python
Yes.
module. Yeah, it's not a good experience anyway. But I mean, for example, Microsoft Office has the COM interface. Is there something similar
Yeah.
for Midas? Because for a complex models, all of these are too many clicks.
Yes. Yes. That's correct. Yeah. The important thing is. In this current version, which is the 2021 version, which you are using, it's 2021, but released just last year. In this version, the API is not there, but we are going to release the API in the next version that will be released in the end of January next year. That means at the end of 2023, you will have the application programming interface in GTS NX, wherein the Python and VBA can be used. Using those two, you can actually play around with the model because when there is a command interface, the developing of the model will be made even easier. So by the end of January 2023, you will be having the API in there because API has already been developed. The only thing is we are doing the other stuff and we'll release it in 2023 and sorry,
That's
2023
great.
January and
Yeah,
yeah,
that's
sorry,
great.
January.
Thank you. One more
Yeah,
question from me. I am not sure. You mentioned the kinds of loads that can be applied. I am not sure if volume loads were mentioned. We mentioned line loads. We mentioned surface loads. Are
yeah.
volume loads possible?
Yeah, so if I think if you talking about volume loads, I hope you're talking about some prescribed strain in the different solids, like you select some solids and you want to provide some volume loss. Is it correct? You are what you are trying to say? Is this one?
So, I mean, for example, a single load is just a load at a point. A line
Yeah,
load is a load along a line, a surface is a 2D load along a
pressure.
surface. I'm talking about a 3D load, for example, like gravity is. I'm talking about a
Mhm.
3D load that is essentially a function not of x and y, is a function of x, y, and z.
Okay, it means you want to apply some spatial loads. So you want to apply
Spatial,
the
yeah,
variation
yeah.
of the load in different way. Yeah, that is possible. So all you can do is like, let's say there is a load here. I would like to apply this load like this. This is changing from first point to the last point. So all I can do is I can simply provide some base function according to the spatial variation. So in which direction it is varying, and then software will apply the variation of that load accordingly. So this is called base function. You can use that base function and you can add a multiplier to that, and then software will apply that variation in the load.
Okay, okay.
Yeah.
Thank you for that. And final question from me. Sorry if I promised it would be the previous. Uh, what about passive loading? So, for example, if we want to simulate soil movement and the effect it's going to have on the structure, are there any explicit tools to do that, or it is up to
Uh,
just applying strains to the boundaries and see how they propagate?
sorry. So, which one you're talking about seismic analysis?
So, for example, let's say you have a load, but you expect the soil to move because of different reasons. You expect a
Okay,
uniform soil movement from bottom to top, linear,
okay,
not
okay,
uniform, a linear soil movement from bottom to top. And
okay.
what is the best way to simulate that? Well, one way is the volume load. That's why I asked about those.
Yeah, yeah,
But
yeah.
is there another way to simulate that?
So the first thing is you can go for prescribed strain. You can apply the strain for the entire thing, and you can, like, let's say, you can provide the strain of something here. But let's say you want to apply the displacement. In that case, we have a prescribed displacement, wherein you can select all the nodes of your model, and you want to move it like let's say of about a 0.005 or that means around 5 mm, or you would like to go for 50 mm. So based on the units, you can apply it. So you can apply it in X direction, Y direction, and Z. You can even rotate that. But for solids, generally rotations is not possible. So you can use this. And even in this condition, you can provide some variation, like from bottom to top. You can apply some linear variation. The like let's say bottom to top is Z axis, and let's say this is Z. And at the bottom, let's say my origin is at the bottom, so I do not want to have any deformation at the bottom. But let's say my top point at this point is like around 50 meters from the bottom. Then I want to have some movement. So this is just a multiple. So when I click OK, I have a general function, and I would like to move this along the X direction. So by what amount, the maximum amount, let's say I would like to go for 0.05 meter. So when I apply this, let's say we'll give the name displacement. So when I press OK, so the entire moment will be there, but this is not actually the 50 mm throughout, but at the bottom it's 0, and as it go on the top it is 50 mm. So linear variation, because you have applied the base function.
Okay, so essentially a volume strain. Yeah, thank you for this.
Yeah, this both are displacement and prescribed strain almost one and the same, because in internally this is the volume loss itself. You have the option to go for prescribed strain, or you have an option to go for the displacement as well.
Makes sense. Makes sense. Thank you.
Yeah. Any other questions? Then I will move to some demonstration.
Yeah,
It
please
will
do,
hardly
Harsh.
take 5 to 10 minutes. Yeah, sorry for that. Yeah. Suppose let's say this is the model that I want to develop. So at first I'm dealing with some soil structure interaction study, and internally, yeah, let's say this is the model of and let's say an integral bridge developed by your structural team, and they have provided some properties according to maybe some analytical theory here. So once this and like a different load combinations, but in this case we have only SITL, sulfite, and crash barrier loads. So we run the analysis, we get the results, and what we need to do is we need to export this entire model for my DES like MXT file, so for GTS or FEA. So when you do this, the entire model will be exported to GTS NX. So once you export it, you will have all these things getting into picture. And this is the model that we imported from IDAS Civil to GTS NX. And along with that, since we have springs applied here, these are the springs, we will even import the spring data here. So these are the springs. So these springs are applied at different points in Midas Civil, and we even imported into GTS NX. But we do not, we are not interested in it because we are creating the entire soil as a continuum, but not as a spring here. So we do not use the spring at any model here. So we will just hide it and we do not activate it in any analysis
Mm.
case. Then this is the soil. And then for the soil, we provide some like advanced model. Like let's say we go for modified Mokulum, which actually simulates non-linear elastic and some hardening the behavior as well. So we'll provide all the parameters, which is very similar to your hardening soil. If you want, you can go for the hardening soil definition itself. So that's up to you with small strength stiffness as well. So you can use this model and you do the analysis. And this analysis will be done for some load, right? So that load will be either an envelope load from the given by your structural team or some very critical load combination given by your structural team. So this has to be again imported, right? So this can be imported using this particular option. You can go to the civil again. You can go to export. That means your structural engineer will go to nodal results for GTSN. So when he do this, all the reactions that you found at different locations here. So let's we'll see the results. We'll Yeah, we will go for some more. Yeah, so all these reactions, the forces, the moments, everything, the reactions over here will now be applied as an like a load here. So the direction will be changed, and this is a resultant force that we are actually seeing. And once this is applied and the soil is generated, so we'll do some analysis, like the static analysis or a construction stage analysis. If you want to do, you can go for a fully coupled analysis. So you can do all the soil related analysis here, ranging from simple static analysis to detailed fully coupled or even seismic analysis. So once that is done, we need to export the force deformation. So once the analysis is done, you will get all the forces, all the deformations at different positions, right? All you need to do is you need to export the nodal results, which is actually the force deformation curves. So we have imported the one load combination here. So that load combination is with the name all. So that is what I have imported, because you can see the name here as well. So CB all, that's a load combination which I have imported. And for that, the force deformation curves will be automatically transferred. So there is no need to take each and every point at a different locations and take the force deformations out of it. So like if you see the results, so you will be finding the deformations. So this is the deformation. You can get the clipping planes. Let's say you would like to see in the X direction. So this is the clipping plane. You can even, so we have many increments over here. So if you want to see in the first increment, you can go here, or else you can simply move this stage bar. So as the load changes, you can see. So in the first stage, just the load of the bridge sulfate has been applied. Then you can go for the load combination or results that you have imported from civil. And as you can see, the deformation changes. So basically with increments, the force and deformation is different. So you can ask the software to take the force deformation at different points, and the software will do it automatically, and it will take that force deformation curves into back to civil. So now I need to import that in civil. As a structural engineer, he will go to the import option, he will go to nodal results, and he will import all the force deformation curves that has been generated from GTS NX to civil. So once he do it, he will get this kind of nonlinear graph, because this is not the same throughout, because at the first point it may be inelastic and at the bottom it might be in a nonlinear. So the region itself is different, right? Because in this software, when you see the plastic status, so some cases there is unloading behavior, unloading failure, reloading, and some cases we have tension failure. And this red portion is a plastic failure. So that means the plastic failure is not like uniformly distributed throughout the model. So from the top to bottom, there might be different of springs that you might have. Suppose, let's say if I go to the first spring, you may have almost linear. If I go to the second spring, you have some non-linearity coming into picture. So it all depends on the type of results that you get from GTS NX. So this will be imported automatically and will be applied at a different position. So if I show you the display, I hope I can display. Yeah, so at different positions, the springs will be automatically applied, and you can the structural engineer will use that results and go for the analysis, and then he will get the results accordingly. And again, he will export the nodal results from civil to GTS NX, and as a geotechnical engineer, we send back the force deformation curves again. So this process may take 2 to 3 times, and then the results will be converged, and then the structural engineer can move for the design. So that's how you can automate it. Generally, in order to send this force deformation curves and so on, it may take huge time and many Excel sheets to be developed, but this has been made automatically using GTS NX. So I hope that is clear, right? Is there any question on this SSI, soil structure interaction studies?
So we can define in the structural model where the springs are,
That's
and
correct,
then and then we import the structural model into GTS NX. And so does this work also for springs under raft foundations, for example?
yeah.
It does.
Yes, it does. It does. Like all the model will be imported, and then what I do is the reactions will again be imported into GTS NX, and that reactions
Yeah.
will now act like an load here. And according to that, you will find the force deformation curves, and that will be exported back to Civil, and then that the structural engineer can use that for the design.
So okay. So the structural model then uses the springs so that they can run multiple load cases
Yeah,
quickly,
yes.
if you like, and design the sections of the various components of the structure, right?
Yes,
Because you
that is
could,
correct.
yeah, okay, yeah,
Okay.
okay. That's quite useful because, yeah, this is yeah, it's quite useful because we're doing this manually at the moment, which is not
Yes,
ideal.
yes. And so if it is all about the queries regarding to SSI, then we will move to the dynamic analysis. So I have made a very small model for that. Okay.
Yep.
Okay. So this is a very small model. What I have done is I have imported the building basically with raft, and actually I have created piles as well. So this is a small building with a pile raft foundation, and this has been imported from Midas Gen, which is general structures as well as building analysis and design tool. And then what I've done is I've created some dense sand and then soft rock in the bottom. And here in this zone, we have a liquefaction layer. So this is the liquefiable layer. So it is susceptible for liquefaction. And then we have a medium sand. So this is not liquefiable, let's say. So what I've done here is, so as you already know, only in the case of seismic analysis, you may find the liquefaction study. So I have in the seismic analysis itself, I have incorporated a material model which will calculate the liquefaction purpose. So there are many material models for liquefaction scenario. We have modified UBC sand, we have a PM4 sand in the model. So I have applied modified UBC sand here. I will just show the input here. So you can go to this UBC sand. So this is the modified UBC sand that I have went for. And so this is in kilonewton per mm, so just the units are a little different now. You can use the type of inputs that you wanted according to the analysis. You can use the plastic cap, means the hardening parameters if you want, you can use it. If you want to have the cyclic behavior, you can go for that. So that's the liquefaction kind of inputs. So once the analysis is done, but in the analysis, we need to have many inputs, right? So for that, uh, you will go to the like analysis. The very first thing is we need to have the type of like a boundary conditions that will be able to simulate the infinite boundary. So we have a free fill, we have a viscous boundary conditions. So in the second, in the next version, you will be having the complaint base at the bottom. So at the bottom, you will be having complaint base boundary. As of now, it is fixed rock at the bottom, but here later on in the next, you will have complaint base as well. But now you can go for the free field condition at the vertical boundaries as well as viscous boundary condition. So this will simulate the infinite boundary by absorbing all the waves that are simulated, that are generated in the model because of the seismic load. And this is the seismic load that I have applied. I went for yeah, this is a type of load, and you can go for either normalized acceleration, or you can go for acceleration. You can go for applied force versus time, or moments versus time. So there are many kinds of function data, and if you want to apply at the bottom, so you need to go for ground acceleration. So this ground acceleration can be applied, and because of that, like since this is a time dependent analysis, we need to apply the time steps. You need to go for how many times you want to run the analysis, 14 seconds, and with how many increments at different positions the software will consider the result. And next important thing is this software needs to have certain damping. So you need to define some Rayleigh damping coefficients. So in this in practice, you need to define it very like in the starting of definition of the material itself. But here in GTS NX, we will define it at the end because we need to have the frequencies as well. So in order to get these frequencies, we will run the eigenvalue analysis here. So once the eigenvalue analysis is done, we, based on the model participation factor, will have the frequencies, and we will use different damping ratios for different kinds of material. So material damping coefficients will come into picture, so that the alpha, beta, basically the mass proportional and stiffness proportional coefficients will be calculated automatically, and this will help in creating the material damping in the analysis, and basically the Rayleigh damping will be done. And now, as you already know, in the dynamic analysis, all the static loads that we apply in the model cannot be considered into picture. So all this static load, the dead load, the floor load, everything cannot be taken into account. All we need to do is we need to convert the entire load into mass. So we have an option for that. So in the dynamic analysis tab, there is an option for load to mass conversion. All you need to do is you need to say what type of load you want to convert it. Software will apply the concentrated mass at that position. So once this analysis is done, you can simply right click and you can solve it. So once that analysis is done, you need to you can see the results, like you can see the liquefaction potential results, you can see the accelerations. So let's see them. At first, let's go for the liquefaction results. If like this is a normalized max stress ratio. If your a model is liquefied, then the value will be more than 1 according to modified UBC sand approach. If the value is greater than 1, then that means this approach, this soil is liquefied. So whenever there is a liquefied thing happening like this, then there will be a change in the bending moment and shear forces in your model, and the moment of your model will also be different. So let's see how the displacements are changing. I will go for the relative displacement. Let's say this is the TX displacement. I will just play a video, but at the first, I will try to go for relative deformation. So this is the like what I'm showing you is the exaggerated view. This is a liquefiable soil. There is a lot of deformation happening over there, and this is how the building is behaving. In such a way, you can even get the let's say accelerations. So with piles, so in the same model, I have analyzed 4 different types of analysis: how the model is behaving without piles, how the model is behaving with piles. So I have the results for different analysis cases. So let's go for with pile case, and let's go for some accelerations. So I want to find the results at the bottom and at the top. So we have 2 nodes, and I don't want the maximum and absolute maximum results. So let's go for table. So you have a step value versus total acceleration. I mean, the total acceleration. So this is not a TX lateral horizontal one. This is a total acceleration. So this is how you do. At the bottom you have the green ones, and at the top, like at the top of the building. So I have selected at the top, right? So this is the second position. At the top, you have a very huge acceleration, which is represented with the red dot. If you want, you can even go for the TX acceleration, wherein you'll find yeah, this kind of graphs. So that means the positive moment as well as negative moment will be covered. So this is a very simple model which I've done. In your main models, you can go for very huge the time of analysis. Like let's say instead of for 14 seconds, you can go for 60 seconds. So up to the the calibration that you want to do, and you can go for more number of time steps rather than just 70 steps here. And yeah, this is a small idea that I can provide. Here, even you can even go for a pore pressure ratio. So this pore pressure ratio is for the maximum pore pressure that you might observe. As you can see, since this is the liquefiable layer, as the pore pressure almost reaches your effective stress, the total stress became 0, and you can see the maximum stress here. This is a ratio, it's not a pressure. But if you want to find the pore stress, you can go to the solid stress results. You can consider the pore stress here. Yeah. So this is regarding to the liquefaction. I will convert this result to meters. You can see the maximum results you're finding here on 255 in the positive direction, and the negative direction 668. So that's how high the pore pressure ratios are. But you can find the results at different points at different locations as well. So in Plaxis, you need to select the nodes, and you want to find the results at different position. But in GTS NX, after the analysis, you can find the results at different points of your interest. And you can actually, this is a stage bar. In each increments, how the results are changing can also be seen. So this will be very much helpful in understanding the behavior of the model in different stages at different points. So that is one biggest advantage. In Plaxis, we need to recall the nodes, and if the results of those nodes are not saved again, that is a problem. We need to rerun the analysis, and that is an issue. So that's how, since all the results are saved in this model, you can get the results at each and every point. Not only the soil results, but even the building results. So you can even get the bending moments. So in Plaxis, generally we only find the results of the soil, but if you want, you can find the bending moment results of your building. I will hide the loops. So the bending moments. This is a maximum exaggerated view. I will go for undeformed state. And this is the actual force. We can find the bending moments. And similarly, you can find the shear forces and so on. So that's a small demonstration about the seismic analysis considering the liquefaction. If you have any question, let me know.
Yeah. So how long would what kind of what time history are you using? How many data points do you have, and how long does it take for this particular
Yeah,
model to run?
this particular model had taken me very less time. I will just show you. Uh, let's go for building. And yeah, so here, liquefaction with piles. Yeah, okay. Without piles. Yeah, so this is without piles. You have a total, this is the CPU time, or this is the clock time. Yeah, this is a clock time which we need to see. So this has taken very less time for me because the model is relatively simple. But this is seconds, we'll divide with So basically 7 hours, 8 hours, we can consider 8 hours.
So what material model have you used? Is it a linear elastic or non-linear
Yeah, I have
soil?
used modified camp clay for the liquefaction layer. For other layers, I have used moculum. So you can see the medium sand I have used moculum, and for a soft rock as well, I have used moculum. And for the liquefaction layer, I have used the other nonlinear material, which is modified UPC sand. So it's not an elastic analysis which I have
Hmm.
taken into consideration, but it's the nonlinear material properties that has been considered in this model. So
What
what I
was the
can share is,
size? What's the size of this model approximately?
you want to see the size?
Yeah, this has
So
more or less, yes, just an idea of the size of
it's a
the model
34
itself.
meters, 34 meters by
Okay.
28, and you can have the depth of around 16.2, and there's a building as well. So somewhere around the Z depth is 37.5. And as you know, it always depends on the number of elements rather than the
Yeah, yeah,
size.
yeah. Then the next question is what is the element
Yeah.
size more or less? Yeah.
So we have many elements in the model. So we have free field elements, we have hexahedral elements of around 58%. We have triangular elements. We have the mass, means all the load which has been converted into mass. We have pyramid elements, tetrahedral elements. So
Sorry.
huge number of elements, and yeah, the analysis has been less. And in order to find the mesh size, you can simply, this is for the soft rock with the very bottom. For this, I have
Hmm.
taken mesh size of 1 meter, but if you go for
Okay.
medium sand, it is 0.75 meter. So at this particular layer, it's 0.75, and it just increased it to 1 till the bottom. So it's quite a good mesh size.
Yeah, yeah, I would say. I mean, what do you think, Manos? You're still there. I mean, you did. How long did it take for your dynamic analysis for the neon tunnels to more than 8 hours, right?
Much longer. And we need to appreciate that this is a 3D dynamic model, not a 2D
Yeah,
dynamic
as
model.
well. Yeah.
So yeah, it's one dimension higher. Well, um, of course, it has to be tried in practice because I
Yeah, of
think
course. Yeah.
yeah, Harsa makes it look too easy, and if so, yeah. So I think that it is much more improved compared to the tools we use. My main concern, because I have worked with Midas in the past, my main concern is that the absence of the API, but this is going to be sorted. So I think it is certainly worth the try. It is certainly worth to invest the time to learn it and actually benchmark it in the machines we use. Because well, we have asked many questions about the model. Uh, Another question is also the machine. Uh, so
Yeah.
yeah, that's really good. Can I take this opportunity for one more question?
Yeah, please go ahead.
I'm a bit interested in how the response spectrum, a given response spectrum from Eurocode, for example, can be converted to dynamic loading, because
I
we do several exercises on that, and that includes going to the database of earthquakes, which you said is already embedded in the software, and doing
mm,
scaling and spectral matching. So, how
yeah, yeah.
how would a given response spectrum be converted to dynamic load?
Yeah, so here for that we have an artificial earthquake. So this is the tool present in the software. What you can do is you can simply generate the design spectrum according to, let's say, Eurocode. I'm not sure whether the Eurocode,
Well,
sorry, which
anyone
code?
will
The
do.
Eurocode.
Anyone will do.
Yeah, there
Anything
is a
will do.
Eurocode.
Yeah,
Yeah, you
yeah.
can simply input the type that you are interested in. And sorry, let's say one, I'm not sure this way. Okay. Yeah, regular. Which one that I missed? Ratio one, let's see. Yeah. So let's say we have this kind of a response spectrum, but let's say if you are not interested in this response spectrum, you can actually import the response spectrum later on as well. So that's not an issue. But let's say you would like to have a time history out of this. So for that, there is some options here. Let's say I would like to go for some iterations. There is a rule called trapezoidal rule. Based on that trapezoidal rule, the response spectrum will be converted back to time history. Suppose the rise time is 1, and the level time, which that means if I go here, let's say this is first. We'll convert this to, yeah. Okay, sorry. Yeah, so this is the rise time, and that will be followed by the level time, and that will be followed by the drop time. So this is the trapezoidal. Like there is some internal mechanism for it. You can actually get to our help manual, understand the internal algorithm, but this is the time which we need to provide. Let's say the level time is 5, and then the total time is, let's say, 8 seconds. Then if I ask the software to develop the acceleration, this is a spectrograph, but I would like to go for acceleration. So you will get some sort of it, but this is very wrong because I haven't inputted the properties correctly. But if you go
Yeah.
for more dimensions, then even you can even find the proper accelerations correctly.
So
Actually,
this
I've created, like, yeah,
so this
okay,
essentially generates a synthetic acceleration that matches the
that's
given
correct.
spectrum.
That's correct. That's correct. But
What
everything has to be dependent on the type of properties that we provide.
what about if someone wants to use not a synthetic acceleration but an acceleration from the database? You don't need to demonstrate that. Is it is it
Okay,
is
okay.
it possible to take a seed from the database and scale and modify as you do with the synthetic one to make them match?
Okay. Yeah. So there is an option for that. So let's go for other model. So we have dynamic. There is a huge list of database that we have. So you can go to the time function, and here we have a database for the earthquake. So we have El Centro and so on. So there are many databases. So let's say we consider El Centro 270 degrees. I think this is vertical one. So once you have this data with you, you can actually go for the base consideration, and there is scale factor here. Otherwise, you can do the scale factor here as well. Let's say you want to do some, or you want to multiply it by twice. You want to change the arrival time by, let's say, 5, or sorry, so it is in seconds. Sorry, 0.02 or 0.05. So you can do the scaling here, or else you can do the scaling directly in the definition of your time history as well.
Okay, is scaling the only way you can modify the acceleration time history?
Like what type of modification that you want? Sorry, I didn't get that. Because
So
this is a linear scale. It will just multiply with the values and provide the scaling.
yeah, well, there's another type of modification that essentially touches the Fourier spectrum so that it makes
Okay.
the response
You
spectrum
want to
of
do,
the
okay,
spectral
now I got
matching.
it. You want to do the deconvolution convolution kind of analysis, right?
Yeah.
Which we generally do it in the 1D ground response analysis. Yeah, for that we have an option called one free field analysis. So this is the free field analysis. So this is more or less like an analytical. It's not a finite element thing. So here you can import the any acceleration that you are interested in. The entire idea is to create let's say we have 10 layers or 20 layers. You need to provide the shear wave velocity and the types of the dynamic curves. So these are the curves, the shear modulus curve, or the damping curve. These are the ones that plays an important role. So once these are applied, let's say this is for layer 1. I'll do this for layer 1 and so on. So I'll consider this layer 1, and similarly I will select all the layers, and I will provide the properties of different layers accordingly, and I will do it like layer tens of layers. So what you can find is in this 1D ground response analysis, you will apply the time history at the bottom of the layer at the bedrock level. And as it goes up, the amplification will be found. But some cases, all the seismograms that we find, all the seismograms, or that means the acceleration time histories, we generally find it at the top of your ground. If you want to convert that like acceleration which you find from the top, like you can apply that seismogram on the surface, and this software will deconvolute it. That means scale down, and then based on these inputs, it's not linear scaling. It's based on the damping curve and the dynamic curve, and using that, the convolution happens, and you will be able to find the like a scale down like acceleration at the bottom. And that using that acceleration, you can apply that at the bottom of like, let's say here, if you can apply that at the bottom, and you can get the analysis accordingly. So basically, that process is called deconvolution.